In this lesson, we're going to examine a different kind of counting technique, something called Pascal's triangle. Now, you may have looked at this in grade 11 last year. If not, totally fine. We'll look at it again. But if you have, you sort of have a good starting point. So one of our primary counting techniques is the idea of patterns. So Pascal's triangle is a specific kind of pattern. There's lots and lots of patterns out there. So, if you ever watched the movie The Da Vinci Code, there's a pattern they call the Fibonacci series. They use in that where they take two previous numbers to add together to make a new number. So like 1 plus 1 makes 2, 1 plus 2 makes 3, 2 plus 3 makes 5, and so on and so on and so on. We're going to look at one of them that we can use in our course for counting paths. This is one of our big patterns. Okay. So Pascal's triangle, how does this work? Well, it's a triangular array of numbers, and it always starts with the number 1. We call that row 0 that we start on. Row 1 has the numbers 1 and 1, and we notice it's making a triangle here. In fact, every row starts with the number 1 and ends with the number 1. They're symmetrical. But to give any other number in the triangle, what we need to do is take the two numbers that are directly above and add them together. So 1 plus 1 makes 2. Or 1 plus 2 makes 3. And symmetrical, 2 plus 1 makes 3. So if I want to find the next rows of this, and I've given you the first 4 rows, and we're starting with row 0, we can figure out pretty quickly. We start with a 1, and then we add 1 plus 3 makes 4, 3 and 3 makes 6, and symmetrical. Start with a 1. 1 plus 4 makes 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5, and 1. And we can keep going and going and going and going. There are some really helpful patterns in this. For instance, if you're to add together the sum of each of the terms in a row, it turns out it always comes out to 2 to the power of n, which is something we've seen before, right? That was our idea yesterday about take it or leave it. If you go back for a second to this example here, row 0 adds up to a total of 1. And then we add up to 1 plus 1 is 2. 1 plus 2 plus 1 makes 4. So if you notice, row 0 is 2 to the 0, or 1. Row 1, which is just 1 plus 1. Row 2 is 2 to the 2. That's your row number, okay? And we had 1 plus 2 plus 1, which, hey, 4 and 2 and 1. Just guessing, if I tried row 3, it should come out to 2 to the 3, or in other words, 8. If we look at row 3, 1, 3, 3, 1, hey, that does indeed up to row 8. So we can ask ourselves questions like, which row has terms that sum to 1024? 2 to the power of what makes 1024? And we can guess and check a little bit and try with our calculators, and it turns out that, well, we're looking at row number 10 then. Okay. Now again, I want to point out our row number always starts at 0. A hint for you, the second term in a row is your row number. So row 2, start with a 2. Actually, I can go even back here, sorry. Row 3 is second term is a 3. Row 4, it's a 4. Row 5, it's a 5. That's sort of a hint about what row number you're looking at. What are some other things we can do with this pattern? Well, by knowing some of the terms, we can figure out other terms, because it's a pattern. That's our whole objective. So for instance, the first 6 terms of a row of Pascal's triangle are shown below. Can we figure out the first 6 terms of the previous and next rows? Now, let's start with the next ones that are easier. So we know it starts with a 1. We know 1 and 16 makes 17. Adding these together, 136. Add these together, 680. Add these together, 2380. And add those together, and you may calculate for that one, 6,188. But I can also work backwards. Again, I know it starts with a 1. And 1 plus what made 16? Well, that's got to be a 15. 15 plus what makes 120? So I can think of it that way, or I can think, oh, I subtract this, I'm left with this. Subtract this, I'm left with this. Subtract this, I'm left with this. And subtract this, I'm left with this. Okay, so I can quickly figure out some terms and patterns, and depending on which part of the triangle I'm looking at, then I can use the idea of symmetry to say, hey, if I know what it starts with, I also know what it ends with. Like the last 6 terms of this row will be the same as the first 6, just in the opposite order, right? Now, why do we really want to use this? What are we going to use it for? Well, turns out that these things, these Pascal values, are actually combinations. Okay? The numbers in Pascal's triangle, the 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, come from combinations. Row number, choose position number. So 0 choose 0 comes out to 1. 1 choose 0 comes out to 1. 1 choose 1 comes out to 1. 2 choose 0, 2 choose 1, 2 choose 2, and so on and so on and so on. So I could actually figure out any number in the table, in the Pascal's triangle, by using combinations. So for instance, if I want to know the 7th row, and I want to know position, I don't know, 3. Well, I can do that. It's 7, choose 3. Right? I don't need to find out all the previous results to actually get an next results because I can use this combination idea. Now here's the tricky part. Remember, things start at 0. So I said 7th row position 3. That's not usually how we call that. We're going to give a row number and a term value. So for instance, I want to find the 8th term in row 17. So what I need to think about here, rows and positions both start counting at 0. So row 17 is obvious. Starts with a 17. I don't have to worry about that. But the 8th term, if you go back for a second here, this is the first term, but it actually starts with a 0. The second term actually has a 1. So yes, this is row 3, which is why these are 3s, but the position, the term number, you actually have to subtract 1, right? Because we started at term 0. So if I want the 8th term in row 17, it's 17, choose 7. If I want the 14th term in row 26, 26, choose 13. Take a term off. 10,400,600. Okay. So I can find specific terms, and we'll use that again down the road a little bit more. Okay, just wonder where they came from. Here's what we're really going to use it for today. It's also powerful in that the patterns can be used to solve path problems. And by path problems, what it means is you start somewhere and you got to end somewhere. So for our purposes, we always have to have one initial starting point. And then we're going to follow a series of paths to the end. There could be multiple ends, but there has to be one starting point. So for instance, this first example here, I want to spell the word math. Well, math has to start with an M, then have an A, then a T, then an H. So if I take Pascal's triangle, I can replace my letters with their values. My starting point, there's 1. I have to start with M. And then it can go this way. There's one way to get there. Or I can go this way. There's one way to get there. And once I get to the first A, I can go to the next T. And I can do that one way. I have to go M, then A, then T. That's a single path. Okay, so I've got 1 here. And the same is true on this side over here. An M, a T. There's one path. But if you look at the middle T, I could have gone M, A, T and followed that path. Or I could have gone M, A, T and followed this path. In other words, there are 2 paths to that. Well, that kind of suspiciously looks like 1, 1, 1, 1, 2, 1. Hey, this looks like Pascal's triangle, does it not? So if we do the H's, 1, 1 and 2 makes 3 in my previous paths. Same thing here, my previous, oops, not that one, that one. My previous paths and my last path, 1, 3, 3, 1. At the end, to figure out the number of paths we could have followed, we take the sum of the values of the finishing points. So in other words, in this case, I need to add up these numbers. So I'll get total paths 1 plus 3 plus 3 plus 1. That gives me a total of 8 paths. That's spell math. Okay, now notice I do want to point out, I'm going to erase all this color stuff here, it's hard to tell. Okay. I can't jump from M, A, T, and then jump over to this H. They're not connected. Okay, there's a disconnect. I can only get to this H or this H by following a path. It's as if you're driving down a road. You can't drive through people's houses to get to the next road, right? You have to go around the corner. Same idea here. So let's try one. I want to spell the word McLean's. Okay, and I have to do an the word order. So what can I do? I can start McLean's with one path, 1, 1. These together make a total of 2. Well, to get to the next L, I have to go from a previous C. So I got 2 here and 2 here, which makes these 2's because I'm now following my previous paths. Okay, so it's not perfectly Pascal's triangle, but it's the idea of Pascal's triangle. The middle, I got 4, and then we got 6 and 6. 2 plus 6 makes 8. 6 and 12. Sorry, 6 and 6 is 12. 8. I got 8 and 12, which gives me 20. And same thing over here. So to spell McLean's in this shape, there's 40 paths. 20 plus 20. Okay. Let's take it to the next stage. What if we actually have physical paths? Well, it's the same idea. Our paths, our picture, we have a starting point, we have an ending point. We want to go directly from one to the other, so we can't like loop around and around and around because that's an infinite number of paths. But I can figure out how many paths there are by using the idea of the Pascal's triangle. I'm just going to make my pen smaller here. I have to start at X, and I have to walk down this road, and I have to walk down this road, and this road, and this road. And I could walk this way, and so on, and so on, and so on. But to get to this corner here, I could have walked this way or this way. In other words, there are 2 different combinations, my results from previous. And I could do that again, and again, and again. And notice I'm adding my previous results, right? Those 2 plus that one. Okay, to the next row, I got 3, and then 6, and then 10, and then 15. And 4, and 10, and 20, and 35. And 5, 4 this way, and then 1 this way. 15, 35, and 70. Now, as I go along the top of this next row here, I've put my 35 from previous. 35, 35, 35, 35. And as I go down, I got my 70s. Okay, the corners, the edges are easy to fill in. But then we got to keep adding again. So 105, 140, 175, 210. 175, we're just adding the 2 previous results, right? The corner to corner. 315. Oh, it's getting harder to use a calculator now. We got 490, and then we got 700, 245, 560, 1050, and then the ones that really matter, the ones in the end, 1750, and 315. 875, 1025, oh sorry, 1925, and at the end, these ones plus these ones come up to 3,675 paths. So if you're driving from X to Y, and you're allowed to take any roads you want to, as long as you don't go back on yourself, you end up with 3,000 over 3,600 paths. Okay. All right, last one. Same idea. Got a picture, but it's got some gaps in it. Maybe there's parks, or maybe there's houses or something like that. But we can apply the same idea, using our previous results to get new results. So my edges, we might as well fill those in right off the bat. And then we'll fill in the parts inside by using our previous results. So I got 2, 3, 4. Now notice I can't go over here and put 5 because there's a gap there. I can't get to that spot. In fact, to get from to here, the only place I can get from is there. So that one's going to be a 1, which makes that a 2. We do a 3, a 6, a 10. Oh, 10 plus 1 makes 11, and 13. 4, 10, 20, 31, 44. 5, 15, 35, 66, 110, 6. Oh, I have to go from here. That's a 6. And then these two will give me 41, 7, oh, 107, 217. And then along the end, 7, 13, 54. 54 and 217 combined makes 273. Oh, sorry, 71. And that's how many paths I can get. So it's a different kind of counting technique. So we're not doing combinations per se, though Pascal's triangle is made up of combinations. We're doing more about the patterning in this counting lesson. Okay. Today's homework, okay, right here, questions to try. It's mostly about the patterns and trying to figure the number of different paths. Hey, give them a try. If you're stuck, come see me.